we're going to discuss some ideas that should make your study of economics easier, more interesting, and it might help you in your study of other disciplines as well. So, in economics and in many other disciplines, we are interested to study the relationship between variables. For example, how does X affect Y? To study the relationship between variables, we can use a concept of mathematics called functions. For example, in this case, we can write y is a function of x. This simply implies that the, the variable y, it depends upon x. So for example, in economics, we can apply this idea in case of the law of demand. Law of demand states that the quantity demanded, it depends upon price, or price determines quantity demanded. So in this case, we can apply the concept of a function and write that quantity demanded is a function of price. So this simply tells us that the amount of goods and services that buyers want to buy, it depends upon the price. An interesting question might arise is, what is the exact nature of this relationship, or what should be the exact structure of the function? In most cases, we assume that the relationship between these variables are linear. In that case, we might use a linear function like this. For example, 7 minus 2p. Although in economics we put quantity on the x-axis, but in mathematics we always put the dependent variable on the y-axis. So we are going to put quantity on the y-axis, and we put the independent variable always on the x-axis. So this is almost always the case. There are certain exceptions only in economics. So in this case, if you graph this function, right, you're going to get a downward sloping straight line. So this tells us that the relationship between these variables are linear, or it is linear. So for example, the quantity decreases always by the same amount for given changes in price, right? But the relationship could be non-linear as well. And in that case, you could use a nonlinear function. So, for example, in another situation, maybe you could have used a function like this. So please note there is a square here, and this indicates that the relationship is nonlinear. And in this particular case, the graph might look something like this. Just a rough sketch. So the graph might look something like this. As you can see, this is non-linear. So this graph is telling us that initially the quantity does not fall that much, but later on, as price increases, quantity falls more drastically. So the nature of the relationship between these variables is actually captured by the specific function, the structure of the function, right? So as another business or economics example, we know that the total cost of a business organization, it depends upon the output. Again, this relationship could be linear, it could be non-linear. So for example, if we find out that this relationship is linear, we can use a linear function, right? So this function is telling us, since the power is 1 here, right, this function is telling us that the relationship between these two variables are or is linear. So for example, if we graph the function, remember the dependent variable goes on the y-axis, the independent variable goes on the x-axis. So this particular function is telling us we have a linear relationship, which means that the total cost increases uniformly for given changes in quantity. Right? We can extract more information from this particular linear function. For example, this number is telling us that the total cost, that the fixed cost is $100, right? And this plus 7 is telling us whenever we produce one extra unit, the total cost will increase by $7. So this is only true for linear function, that this number gives us a very interesting piece of information, that if the independent variable, if this increases by 1 unit, then the dependent variable total cost will increase by this amount, right? $7. So the total cost increases by $7. So this information is only applicable for linear functions. So that is one benefit of using linear functions. Now let's cover some other interesting cases, because you're going to see these again and again. And if your foundation is strong, I think your study will be easier and more interesting. So in economics, we assume that the output of a business organization depends upon inputs, namely labor and capital. Simply, the amount of goods and services we can produce depends upon the number of labor we have and the number of machines or capitals we have in our business organization. So the next question is, what is the exact nature of the relationship between inputs and the output? Right? How are they related? So let's do a graphical analysis. As we learn in basic economics courses, that there is a very interesting relationship between the input and the output. So let's choose one particular input, let's say labor. How does it affect how does it affect the output? We know from basic economics that initially the output increases rapidly, but later on the output increases, but it increases by lesser and lesser amount. So this graph is telling us that initially the output increases more, later on the output increases much less. So definitely this is a non-linear relationship. How can we represent it mathematically? Mathematically, it is actually represented by using a power of less than 1 and greater than 0. So for example, in most of these functions, you're going to find a power that is less than 1 and greater than 0. And this ensures that we can capture this relationship, which, as you might remember, is called the law of diminishing marginal returns. And that is applicable for capital as well, right? So this is how we can use mathematical functions to model and study the relationship between variables. And most likely these ideas will make your life easier, and your study more interesting. So perhaps I can just cover one more topic before we wrap it up. Um, in case of most functions, so you might see another number here in front, that's just a constant, right? Most functions will have some constant. uh, Anyways, so there's another interesting idea which I think I should just briefly cover. So the idea is that, every function, well, let me correct myself, most functions um, have derivatives, or you can find the derivatives of most functions, right? For example, you can find the derivative of this particular function, and this derivative is denoted as dy by dx. So what does the why is the derivative important? What does it tell us? Well, the derivative gives you an idea about the nature of the relationship between the variables. Again, right, it comes down to studying the relationship between variables. For example, if you find out that the derivative dy by dx is greater than 0, interestingly, you can conclude that these two variables, right, these two variables are positively related. So for example, if x increases, then y is going to increase as well. Or remember, the opposite can be true as well. So if x decreases, y will decrease as well. So if you find that the derivative is positive, then you can make this conclusion, right? uh, so for example, if you find out that in a certain situation the derivative is negative, right, definitely now you can conclude we have a negative relationship. So I'll discuss this here on this side. You have a negative relationship, which means if x increases, then y is going to decrease, or the opposite is true. If x decreases, y is going to increase, right? So just by looking at the sign of the derivative, you can get some idea about the nature of the relationship between the variables. Interestingly, sometimes we might even want to find the second derivative, right? So we can differentiate this derivative, and we can find the second derivative. Interestingly, the second derivative has this particular symbol. So what does the second derivative tells us? Again, it gives you more additional information about the relationship between the variables. For example, if you find out that the second derivative is negative, this actually tells us that, this variable y, it increases. Initially, it increases at a faster rate, but later on, it increases at a lower rate, right? So, more precisely, if you find out that the first derivative is positive, and then you find out that the second derivative is negative, so it indicates the situation is like this, right? Initially, the y variable, or in this case the quantity, will increase by at a faster rate, and later on it still increases but at a lower rate. So as you can understand, the derivatives give you even more additional precise information about the relationship between variables. um, so what about the situation where you find that the second derivative is positive? I think you might be able to guess this. So we cannot actually make any solid conclusion by only looking at the second derivative. We also need some information about the first derivative. So remember, the first derivative, if this is positive, right, so this tells us we have a positive relationship, right? So if x increases, y is going to increase. We are going to have a upward sloping graph. But what about this second derivative? What additional information is it giving us? Well, it is telling us that initially x increases at a slower rate. Later on, it increases at a faster rate. So uh, I hope you can see the connection here. So this tells us we have a positive relationship, right? Definitely x increases, y will increase, we have a positive relationship. But what is the exact nature of the positive relationship? The second derivative tells us that initially y increases much slower, and later on y increases much faster. So the second derivative is positive. um, so that's it. That's the end of this particular tutorial. I really hope it will make things easier, university education and particularly economics education. Thank you for watching. I'll stop the recording here.